will start in 7 minutes. They will be here. Okay, where we are. Where we are. Time to do something. Yeah. Time. 4 minutes behind shadow. Okay, let's continue our distance protection saga. Next moment, there is one problem with distance protection. It's called synchronous swings. You have, let's say, system 1, connection, I'm simplifying, system 2. When everything fine, both systems work synchronously, everything nice. But what if, for example, you had parallel connection and it failed? What may happen? May happen problem when your transfer capability between systems is too small, too short to transfer power. And what will you get? Asynchronous regime. In worst case scenario, there will be situation like this. When worst case scenario, when systems EMF are fully opposite. it's a disaster. Potentially. Here somewhere in connection will be point with all zero. And this is called of electrical swing center. Center of electrical swings. Point where voltage is zero. During series electromechanical transients, very serious problem may happen. In both cases, you get voltage zero. Ooh, you in deep problem. Because your distance protection will assume a free-phase fault in this point. For distance protection, center of swings is equal to free-phase fault. Your protection will, if you miss this, your protection will operate and cut your last inter-system transit. It's a disaster, real. To prevent this, any distance protection should be immune to synchronous swings. Early versions used criteria plus negative sequence presence was used to criteria as criterion to unblock distance protection. Distance protection was blocked until this criterion met. It is not reliable. Faults observed, real faults observed, when simultaneous free-phase fault occurred. How? 110 kilovolts tower stands in the middle of the field. Farmer don't like missing part of his land. So he used this tower as a storage place for fertilizer. In short time, earthing, roads, everything, all this corroded. Absolutely. And when lightning strike, all tower rise in potential above ground level. And all three insulators were overshot instantly. So instant free-phase fault. It's seen in reality. No, this old technique with negative sequence is not reliable. It was generation 1. Generation 2 relied on think like this. Operational zone, let's say 3. Additional extra zone. So, during the fault development will be 2 trips. One on external zone and one on internal. Time between these 2 trips, it's a trajectory of fault. Delta T, time difference between 1 and 2 events should be less than approximately 1 second, because swing, this asynchronous mode. What about system? Have you heard on system dynamics? Zitzman's course. system dynamics.
Mm-hmm.
And nothing about electromechanical transients. Okay, but it is in program. We have a course on transients. Inga Zitzman reads, Professor Zitzman. Where am I? What I'm doing? So, 2 trips, external, because electromechanical processes are relatively slow. Faults, short circuits are fast. So within 1 second should operate. It's a generation 2. Generation 3 is bit more adaptive. Also, there was a kind of the criterions. It's the same. Modern industry standard is operation on how the modern standard relies on impedance derivative, and very common schematics is not round, but something like this. It's a set of 2 zones. So, pre-fault is somewhere here. This is some point of, this is alpha. So, during the transient, it's fault developing. There again will be 1 and 2 trips. Time difference 2 minus 1. So time difference between them should be less than predefined time threshold. It gives us derivative of the impedance. Why such zones? They are from straight line because it's faster to calculate, and there is one idea behind it. Its idea what during the swings z minus z this point these lines are possible trajectories. They close it as a circle, also like this. So this one are forward, and this far, when you trace impedance point during synchronous swings, if they are not going to full this worst case, but only swinging, it runs somewhere in kind of circles around line ends. If you go in deep analyze, at some moment you can have picture like this. Around 0 point, when you will take this transient curves, you may ask for trajectory of observable resistance. May have something like this. It's a probable, and to get some kind of approximation, chart, it's a kind of approximation to these possible areas. First, it's developed by Siemens. Now it's become kind of industry standard to determine speed or rate of change of resistance. If it will be your job, you need to ask guys on system stability, those who are responsible for system stability, and ask them to calculate possible swing. They can give you these arcs, upper and lower. So with the help of this arc, you can you can define this upper and lower margins. If not, simple dance from the load regime. But I'm only pointing my finger. All distance protection can operate falsely in case of asynchronous regime, in case of synchronous swing. So they should be blocked and unblock or elbow only on basing of or rate of change, or plus if you see negative sequence current voltage, okay, you can operate. In theory, what kind of theory? As the digital models do exist, I read the protections able to operate during swing, during this electromechanical transients, but I never heard or seen them in flash. In model, yeah. As a scientific concept, yeah. As a device, never seen. Okay, it's a problem number 1, synchronous swings. Problem number 2. Problem number 2 you will face is so-called zone shortening. Here's fault. You sit here. Here is your current, I1. From this point flows I2 to the fault. Yeah? Yeah. Okay. What you will see? In theory, you should see V1. This is protection, point where protection sits. Like this. Let's assume it's inside your this is A1, let's say this is A2, and here is point of fault on at a distance alpha. Okay, that's what you should see. Maybe why it's no protecting. protected by the, let's say, here is 0.6 of length. So my fault is protected. Here is my fault. Oh, place of fault. Very fun. Yeah? Very nice. What happens in reality? In reality, I have second current. Voltage drop from second current flowing to this line point will shift what will happen? This point, this part is I multiplied by alpha. And here is my I would say resistance what will see my protection. Because of second current. Flow of second current from second source shifts observable point forward. This effect called zone shortening. Current distribution factor is ratio between fault current and current seen by my relay. So it's current of relay divided by fault current. Here I have this current distribution factor ZA less than 1. Only part of fault current flows through my relay. This causes faults in second zone appear in third. This causes delayed backup operation. It's not, I would say, hampering on line operation, but it causes delays in backup operation. It's not a disaster, but some system operators require to check for this, and they require, codes require safe operation of backup protection, what in say, operation within permittable by system, time permittable by system stability. So this condition should be checked. Some scholars, some engineers propose to create settings on the basis of real, not real, but most probable current distribution. So they will propose to draw a two border here. It's a very dangerous practice, because in case this, for example, this generator is unexcited or not operating, in case you shift upper border here, you will get non-selective trip of your second zone. It's a danger thing. So should be extreme care if you are pushed to calculate settings on the basis of more, not when current distribution coefficient factor, call it your name, not one, be very careful. Ask, if you pushed to do so, ask for paper. It's a real dangerous thing. But you should understand, what in case of backup operation, current distribution, real current distribution, pushes observable point of fault forward, meaning what your second zone as a backup zone will be shorter. Next, parallel lines. And external fault. This problem persists only in case of earth faults to the ground. So, your parallel lines are coupled with metal inductors. Real significance is only on zero sequence. Here, I1, I2. Only significance is in zero sequence. As I draw it, current from second line through metal inductance will what? What it will do? It will induce voltage drop increasing line resistance. So this current increases line resistance. For your protection, what will happen? Observable fault will move forward. So resistance increases, fault moves outside. Also may cause delay in backup operation. But this is not a disaster. Actually, modern protection terminals offer one interesting thing. You can take zero sequence current from your parallel line and use a so-called compensation channel. Real modern terminals allow you to take zero sequence current from your parallel line and compensate this error. It's more needed for fault allocation, but you can use this feature. So in this case, if an external fault, observable resistance increases. This causes possible fault from the second zone shifts to third. It causes delays in operation. Internal faults. Only zero sequence coupling counts. Only in zero sequence schematics they should be accounted. In such kind of schematics, parallel lines, in case of internal fault, there will be a path with opposite current flow. In the path where current flow in opposite direction, observable resistance decreases. It's called decrease in resistance. And for this relay, fault moves closer. For this one, moves forward. it is possible that you will get strange behavior. Not operation of those not as intended. One of the things you need to check is for cascade operation. So if for this relay resistance decreases, it will see closer. So fault moves forward, this relay works faster. When this relay, this trips, what happens? This round current disappears, and all fault current flows here. This current increases, and operation conditions for protection here will be better. It's called cascade operation. When first for example, around middle of the line, approximately, for this relay, observable fault place shifts closer, it operates faster, interrupts this current loop. For this relay, current increases and it operates in better condition. This is allowable, but you need to check on model what it really works. In our practice local, it's allowable, it's not a crime. You just need to know, remember this moment. Next, same thing with parallel lines. We have set of parallel lines, but one of them is disconnected and asked for repairs. Only zero sequence mutual inductance counts, but here be prepared. You will get current, one, circulating current, two, through the ground. This current decreases observable resistance of this line up to 30%. For repair conditions, settings of distance protection must be recalculated and changed. It is serious. When parallel line is switched off and grounded, coupling between them still remains. In normal regime, this coupling isn't very serious. While linemen sometimes, hey, come on, it's current here, we see current. It's induced. But in case of earth faults, this coupling will be serious. Before line goes for repair, you need to prepare set of settings for repair mode. And it should be calculated a 25-30% decrease in line resistance. Be prepared. This point is serious. Okay. Next moment, you need to know. You need to be prepared. Effect of power transfer. goes from system 2 to system 1, and you have, for example, nice earth fault. I don't know, for example, this is alpha ZV. Power transfer on Z will cause shift. This one is caused by power transfer. To prevent misoperation, from 5, 10, maybe even 15 degrees angle is added to the left border of characteristic. While this one has our line angle, actually you can slope it a bit. It's from nature of arc. The higher current to arc, the less is arc resistance. So at the end of the line, current will decrease, and you may add bit angle, because probable transient resistance at the end of line is a bit higher than at the beginning. But it, never mind. But for prevent misoperation due to power transfer to the phase, angle, in characteristic angle from 5 to 10, what I'm doing, degrees, it's needed. Okay, it was a simple part. Now more complex. Complex part. Let's say we have faulted distance of with a transient resistance of Rf, and we have this is I1, this is I2, current from the opposite side. At the first glance, here is vector of my line resistance. Let's say this is line at 0,8. Here is my point of fault. This is alpha ZY resistance. Very nice. Need to add, this is RF. I'm adding fault resistance. Fine. But that's not all. Current from the opposite side flows to resistance. If there is a situation where no phase shift between line, it just adds, this part is I2 RF. In reality, there always is a possibility for power transfer before fault. And we will get something like this. Appears these parts are I2 RF. Direction and length are dependent on fault resistance, and they are very dependent on angle between systems. In reality, it's a transfer. It's a function of transfer power before fault. As you see, they can go up and go down. Actually, you need to calculate. You cannot tell 100%, but possibly up goes if you transfer from system 2 to system 1, and down if you had transfer from system 1 to system 2. It depends on angle. That's why this line, see, I draw this line multiple times without explanation. This line has an angle because in case of transfer this way and 0 kilometer resistance, it is possible that fault vector will be somewhere here. It will be shifted down by current from opposite side. I have a good research on my disposal. One moment, I will get it to it's a work, it's one student's master thesis. 1 second. One moment, I will connect my TV. Master thesis by Sergei Sheikin. It's called influence on distance protection from transient resistance. I was scientific advisor 10 years ago written. Yeah, but what do we need? It's kind of blah. 1 second, I will find. Here is chart. See, these are possible regions during. Yeah, that's what I needed. It's an actual fault record from 110 kilovolts line. 3 falling on a line. Phase current 0 sequence. Here is calculated resistance. Green line is full resistance, blue reactive part, active part. See what happened? Next one, tumor candle. It's a pine tree for, on the pine tree on 110 kilowatt line. See how current growing? It's a character for local trees. They are not burning instantly. For some time they withstand line voltage. See, it's 0 sequence current and this is voltage. Here is chart of of observed resistance. You see active part going down, reactive in some area. Do you see what happened with reactive? it was negative. While this tree burned. One more. It's a birch tree. Again, see, steady growing. That's what happened with reactive resistance. At early stage, because we have large transient and power coming from opposite side, we see negative reactive resistance. One more. Yeah, tree disappeared. See? Again, a small negative. So the one more ups. It's elm tree. Again, see how it burns and how observable resistance changes. I can go forward to the modeling. We open here. Look. Here, what we see is a development of transient during the burn of its modeled transient with increasing transient resistance. With assumed transfer angle 60 degrees. You can see this is how changed resistance observed by protection. More serious, 60 degree and inflow from distance. This point is a trajectory. Protection relays will see while this tree burning. So this means what? First, delayed operation, and second, if you make a mistake and you don't allow fastest zone to operate, if was delayed zone started, you will get delayed operation. It's what happens. Also, I need to point with finger. If you have criterion, it's transfer from opposite side. If you have criterion derivative of resistance or resistance rate of change, in case of burning tree, if you select this time interval too short, your protection will not operate because resistance changes slowly. It's a problem. Actually, local practice is to set a backup earthfall protection for such case. Okay, you saw this one. Yeah, one more. Inflow, 60 degree transfer angle, and we, in this case, we as system 1, not we, but system 1 sells energy to system 2. This case for import. System 1 imports energy from system 2. That's what will happen during the tree burnout. It's again problem of distance protection. Okay, zero, near zero transfer angle. Okay. next moment. What's next? 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 Fault in voltage circuit. If one of the voltages disappear due to fault in secondary circuit, protection will operate firstly. To prevent this, special circuit is implemented. It prevents protection operation in case we have zero negative sequence voltage but do not have negative sequence current. It's for fault in voltage circuits. Yeah, but that's not all. What I need to draw? Yeah, I need to draw blind zone. Distance protection are vulnerable for blind zone. For problem of blind zone. What is it? Not important. Fault. What's the problem of blind zone? Distance to fault. Why it's not right? Current. Voltage available to relay. There always is a minimum 3 voltage for relay to calculate resistance. If voltage is less, relay can calculate anything. This, you see, this part of line will be unprotected because it is not possible to calculate resistance. It's a problem. For many relays, characteristic has a blind spot at a 0 kilometer. To prevent unprotected line, what's done? First, second generation relays were equipped with memory circuit, resonant contour powered from third phase. For example, if we have AB voltage relay operating with current AI minus AB, C phase was used to power this resonant circuit. In case AB voltage disappear or is lower than the operation threshold, contour remembers, it's a memory circuit, keeps for some time direction of C0, of C phase voltage. It's used to determine direction. So Gen 2, second generation relays, do fall into, in reality, they become directed over current relays. Generation 3 relays, digital, had a memory for operational voltage. If voltage is below precise operation threshold, voltage from memory used to determine direction, relay become polarized. Not a very safe thing. Why? Why it's not safe? Switch on fault. This is this danger only waits us in case of three-phase fault. When you can get three-phase fault on zero distance. Your lineman left earthing link. Lineman, mistake. It is probable, it's highly probable. Because of miscommunication between contractor and dispatch, lineman still working, dispatch get command to switch line on. And you get fault on 0 kilometer, at 0 distance. In such case, switch on fault, there will be nothing in relay memory and memory function become useless. Where to run? It is mandatory to back up your distance protection with non-selective overcurrent protection. It's mandatory. So you have distance protection model. In parallel, it's mandatory from this normal close contacts. Timing relay. What's this? Instant overcurrent protection. Active for time max 1 second. Maximum it should be active for 1 second from the moment. How this will work? When switch is off, time relay is energized. These contacts are closed. When switch is on, relay is disenergized, but the circuit for instant protection remains active for 1 second. It's a mandatory thing. Non-selective instant protection, protecting on, it should protect only 10% of line, 0 kilometer. It should overlap blind zone of distance protection. Should be activated for short time, only for 1, maybe even less than second. It should be active while till the time distance protection will fill its memory. After that, it will operate directly and this overcurrent protection is no longer needed. But for switch on fault condition, distance protection will fail if you have switch on fault at 0 distance. To prevent it, non-selective overcurrent protection activated for short time after switch is on. Should remain active for short time after switch is on. It's a mandatory thing. Or prepare for a serious problem. What's next? Fail of distance protection is a serious fail. It's not couple of customers. It's maybe city. What else? What I forgot? What I forgot? To decrease damage of fault. If you have distance protection on both sides of a line, and it is a communication infrastructure, use trip signal propagation. If you have fault in first zone of this protection, distance protection, trip signal should go also to distance protection 2 and act and immediately transfer here. This to reduce, if on the one side we have trip of first zone, on the other side it will be second, do not wait. If first zone activated, send the signal through the communication infrastructure if you can. One more moment. In case you have substation, for example, in the middle, the same care about zero sequence impedance should be taken as simplified substation. Here, same care of zero sequence impedance should be taken as it was for earth fault protection. Only one transformer grounded. Grounding of both elbows only for when connected to net or disconnected in long loops with higher voltage network connection. In the middle of loop, no neutral is earthed and off. This what should be, this measure should be mandatory. Oh, Spain and Portugal are in blackout. Major power outage. Oh yeah. Large part of Spain and Portugal, including capitals Madrid and Lisbon, have been hit by power outages. Not clear what caused. Yeah, surprise. Power cut. Do careful. Calculate distance protection settings, or power outage may occur. False operation of distance protection is a possible cause for such disaster. Okay. What do I need now? Time is up. Spain without power. Okay, I will and